Hi everyone, thank you for joining us. Today's webinar titled Smart Evaporation for Modern Laboratories. My name is Christoph Killman and I'm the Business Development Manager here at Porvay Sciences Limited, known as PSL. I have been with the company for quite a few years now, and it's great to have you joining us today. Speaking along with me will be James Edwards, our chromatography manager. I would like to also mention that during this webinar, you can ask any question and post them into the chat. We will address them during the Q&A session at the end. For those who might be new to PSL, we are part of the Porvay Life Sciences Group. We focus on developing innovative solutions for the life science, chromatography, instrumentation, and automation markets. At PSL, we have an experienced team capable of delivering bespoke projects supported by a large R&D department and over 45 years of expertise working on major projects with OEM partners. We are currently progressing through our rebranding process, so you will see our name and logo appearing more frequently across our marketing materials, reflecting our dynamic approach to innovation and continuous improvement as PSL. From an evaporation perspective, PSL is a market leader. Our ultravap evaporators are designed and manufactured in the UK and are among the most widely used evaporation instruments on the market, particularly by the system integrators due to their automation-friendly design, reliability, and ease of integration into robotic workflows. PSL's ultravap range is designed to provide efficient and reproducible solvent evaporation across a wide variety of laboratory workflows, from low-throughput benchtop use through to fully automated high-throughput environments. All ultravap systems are blow-down evaporators using a control combination of heated gas and temperature to gently and consistently remove solvent while protecting sample integrity. The portfolio has been developed to support standard labware formats, providing predictable performance and ease of integration into robotic workflows. I will start with the UltraVap Mini, which is our most compact entry-level system. The Mini is designed for low-throughput laboratories or users who need a simple, reliable evaporation solution for tubes or small batches of samples. It offers controlled heating and gas flow in a small footprint, making it ideal for manual workflows, method development, or laboratories with limited bench space. Next, we have UltraVap Gemini, which is a step up in terms of flexibility and capacity. The Gemini supports both tubes and microplates, making it well suited to laboratories running mixed sample formats. It provides improved control over evaporation conditions and higher throughput compared to the Mini, while remaining easy to operate in a manual or semi-automated environment. This makes Gemini a popular choice for analytical labs transitioning forward a higher throughput where automation isn't yet required. Moving further up to the range, we have the UltraVap Levante. The Levante is designed specifically for microplates-based workflows, and it's commonly used in a drug discovery, analytical chemistry, and a sample preparation laboratories. It offers uniform evaporation across all wells, helping to improve reproducibility and consistency between samples. This system supports higher throughput and is frequently used in semi-automated environments, making it a strong fit for labs that require performance and scalability. The Ultravap Mistral is our next instrument, is a flagship automation-ready evaporator. The Mistral is designed for a high-throughput laboratories and is widely adopted by automation integrators. It supports rapid evaporation of microplates and tubes with precise control over the temperature and gas flow, making it ideal for fully automated workflows. Also available in a large version with capabilities to run glass vials and large plates known as Mistral XT150. Because of its robustness, reproducibility, and integration-friendly design, the Mistral and Mistral XT150 are often the system of choice in a large pharmaceutical, CRO, and automated screening environments, and it's also the platform used in the evaporation case study you will see later on this webinar. So that's it, a high level overview of the Ultravap portfolio, from compact benchtop system through to fully automation compatible high throughput evaporation platforms. Next, we will look at why evaporation matters in sample preparation before moving into the technical data and demonstration. I would like to hand over to James Edwards, our chromatograph manager, for a minute to step back and answer an important question: why good evaporation matters and why getting this step right can make or break a workflow. James, over to you.
Thank you for that, Christoph, and giving a good overview of the different Ultravap evaporators. So having effective sample preparation is an important part of an analytical workflow. It can have a big impact on the data before samples even touch the instrument. The way we clean up, concentrate, and prepare a sample will really determine the quality of the final data. And evaporation forms an important part of that sample prep workflow, ensuring that solvents are removed in a controlled and consistent way, leading to more accurate downstream analysis. So some of the advantages of good evaporation include reducing your sample volume to concentrate your analytes in the solution. This boosts the signal to noise of a peak and therefore increases detection limits, which are often linked to signal to noise values. Without concentration, analytes may be missed or methods may lack the sensitivity to pass validation, especially if there are very low limits of detection. For example, PFAS testing, where there are parts per billion or parts per trillion limits of quantification, which typically will require some form of concentration. Uniform evaporation is a result of stable temperature combined with controlled gas flow. This ensures that each sample is processed in the same way every time, reducing your run-to-run variation and leading to more confidence in your workflow and results. Evaporation isn't just about getting higher sensitivity though. It can allow an analyst to perform solvent exchange or adjust the solvent composition. This is very important when the solvent after sample preparation is not suitable for the instrument method. For example, running a non-polar solvent like hexane on a reverse phase HPLC method with water, the two solvents won't mix and the result is very poor performance. Some of the disadvantages if you have poor evaporation include when you have harsh evaporation conditions, so too hot, too long, or too high of a gas flow. It may result in analytes being lost if they're volatile or not thermally stable. This can lead to inaccurate quantification, poor recoveries, and lost time trying to investigate what went wrong. If the conditions are right, but they fluctuate during evaporation, this will introduce variability across the samples or run-to-run. This can lead to analyte responses varying and impacting method robustness. Some evaporators may also make it difficult to set the height accurately or precisely. This is another area where you can get irreproducibility, as the rate of evaporation will vary depending on the distance from the gas from this to the solvent. If the gas flow varies, it may result in samples splashing within the sample container, be it a plate or a vial. This can lead to sample being blown out of the container and into other vials or wells, resulting in crosstalk. which is contamination of sample from distribution of it into adjacent vials or wells. Finally, if your evaporation is not set up optimally, you could be reducing your throughput through longer evaporation times within your sample preparation workflow. So there's three main types of laboratory evaporators: centrifugal, rotary, and blowdown evaporation. First, I'm going to talk about centrifugal evaporators. These evaporators apply a vacuum or centrifuging sample. This allows the pressure within the evaporator to lower and therefore reduce the temperature it takes to boil off the solvent. With it being a centrifuge, samples do have to be balanced with the correct composition of solvent. This is because different solvents will evaporate at different rates, causing the centrifuge to become unbalanced during evaporation. This can make it a lot less flexible when evaporating samples. For example, you may need to fill another plate, which is just waste, to evaporate one plate. These evaporators can also have quite a few parts to maintain, so a condenser, vacuum pump, and the seals. This means they can require maintenance to make sure they're running at full effectiveness. There's also a risk of cross-contamination with samples being in a shared vacuum chamber. So if solvent condenses within that vacuum chamber, it may contaminate other samples in that vacuum chamber. Rotary evaporators, they're typically designed for larger volumes, so usually liters of solvent. So they're not typically used for drying samples before chromatography analysis. Like centrifugal evaporators, they use vacuum to reduce the boiling point of solvents and are combined with a water or oil bath to heat up the solvent up, increasing the rate of evaporation. The disadvantages of rotary evaporators are that they're low throughput, typically designed for one container, which makes them not suitable for large numbers of samples. The evaporation can also sometimes be quite vigorous, which may result in bumping, which is a sudden or violent evaporation of solvent, which may cause splashing or loss of analytes. They're also not designed for small volumes of solvent, as I said before, so it needs to create a thin film of solvent within the flask. Therefore, they're not typically working well at the low milliliters or microliter volumes. Blowdown evaporation uses a controlled flow of gas, usually nitrogen or air. Nitrogen is the most common gas, as air can cause oxidation of certain air-sensitive analytes. The gas is directed down onto the surface of the solvent, and the height of the needles from which the gas is delivered can be changed to follow the solvent front and maximize the surface area of evaporation. There's also the option to heat the gas, which again will increase the evaporation rate. I will discuss these two evaporation variables, so gas flow and temperature, in more detail shortly in a study that we performed. Blowdown evaporation can be carried out on a range of different samples and formats, so from well plates of all sizes, 24 to 384 well plates, autosampler vials, or even larger glass vials. This type of evaporation is what the PSL's ultrafat range of instruments provide. So we wanted to understand more about how much temperature and gas flow impacted blowdown evaporation. So we performed a study to look at how we could create more efficient methods for common chromatography solvents, which would improve the evaporation workflow, saving analysts time on evaporation during their sample preparation. Using our ultrafat Mistral, we're able to program in different temperatures, gas flows, and program in needle heights to keep the distance from the needles to the solvent consistent as solvent evaporated. So we first looked at temperature, and as you would expect, the higher the temperature, the faster the evaporation rate was. What we noted was that the largest overall percentage increase in evaporation occurred between 30 and 60 degrees Celsius. However, this has a larger temperature difference compared to going from 60 to 80 degrees Celsius, so 30 versus 20 degrees Celsius. So when you accounted for the percentage increase per degree Celsius, most solvents had a lower percentage increase in growth in the 60 to 80 degrees Celsius jump. There was one exception to this, which was 100% methanol. And with that, we noted that methanol has a large increase in vapor pressure at 75 degrees Celsius, which the other solvents didn't. So this was likely the cause for this exception, as vapor pressure is a direct measure of how likely a solvent is to evaporate. So a higher gas flow increased evaporation, and this was the case across all the different temperatures tested. One interesting point we did note was that for mixtures of methanol and water, from 25 to 75%, increasing the flow from 55 to 75 litres per minute had less of an impact compared to 100% methanol. Mixtures of methanol have a higher viscosity than 100% methanol, and the most viscous solution, 50% methanol, had the smallest difference in evaporation rate when changing a flow rate from 55 to 75 litres per minute. This suggests that gas flow will always increase evaporation, but the more viscous a solution is, the less impact increasing gas flow will have on evaporation. Another interesting observation we made was that methanol and acetyl mixtures with water act differently during evaporation. An example of this can be seen in the plot on this slide, comparing the evaporation plots of 50% acetonitrile and 50% methanol. On the x-axis, you have cumulative evaporation time, and on the y-axis, you have the average solvent left in each well. For the acetonitrile water, evaporation has two profiles with different rates of evaporation. The first is likely where the acetonitrile from the mixture evaporated off, then the second section with the remaining water evaporating off. Whereas for the methanol water mixture, there was a more curved evaporation rate. This was likely due to water forming hydrogen bonded clusters with the methanol, and breaking these bonds requires more energy and slows evaporation, preventing methanol from evaporating separately to the water. Whereas acetonitrile forms fewer hydrogen bonds, which results in a weaker cluster formation, giving the two separate evaporation profiles. So this is an evaporation plot similar to the one on the previous slide, but instead it shows the full range of experiments that we performed on 100% water. To note is that the evaporation rate is consistent, showing a very linear line. There is a slight curve off at the very end of the evaporation. This is due to the bottom of the well plate having a pyramid bottom. So as the solvent approaches the narrower bottom of the plate, it reduces the surface area of the solvent, which in turn reduces the rate of evaporation. The study has identified some helpful insights in how to optimize evaporation. For example, if you have a temperature-sensitive sample and need to run at low temperatures, then if you use the higher flow, so 75 versus 55 litres per minute, and you're evaporating water, it could save approximately an hour. If you can run at higher temperatures, as your analytes are stable at those higher temperatures, then going from 30 to 80 degrees Celsius could save approximately 2.5 hours per run. Our Levante and Mistral evaporators allow you to program in needle heights at time intervals, allowing the needles to move over the course of an evaporating run. So based on volume of solvent, density, collection plate dimensions, you can figure out this height of solvent within the well. Therefore, if you combine this with the known height of solvent with the programmable needle height movements, you can follow the solvent down the collection plate as it evaporates. These plots and the data that it gives can help give better indications of evaporation rates to predict solvent heights over a run. This can be very helpful when creating new methods to evaporate different solvents in a range of well plates or even at different volumes. So to conclude, temperature significantly affects evaporation, and a higher gas flow rate also increases evaporation rates at all temperatures tested. However, this effect is smaller for more viscous solutions, for example, 50% methanol water. Acetyl water and methanol water solvent mixtures show differences in evaporation, with acetonitrile water having two distinct evaporation profiles, whereas methanol water showed a curved trend likely due to hydrogen bonding and cluster formation. Optimized methods can be developed from the experimental evaporation rates for a range of collection plates and volumes. And the ultravac Mistral gives consistent evaporation rates over the whole run, shown by linear evaporation rates from the previous plots. If you wish to hear more about this work, the full application note can be found by scanning the QR code in the bottom right-hand side of this slide. So we're now going to move on to our live demonstration of 3 of our ultravac evaporators. So we have the Mini, Mistral, and Mistral XT150. Christoph will be demonstrating these and showing how they're easy to use, show the flexibility of how they can be used for plates and vials with the different needle head formats. So with that, over to you, Christoph.
Okay, thank you very much, James. And obviously, I would like to welcome all of you one more time from our R&D center in Wrexham. This is the place when we're testing all our instruments and obviously we're doing our application notes. So in this ultravac mini demo, I will focus on practical checkpoints you would use in your own lab. Watch how quickly it's ready to run, how it's easy to set temperature and gas flow, and how you adjust needle height to suit your plate or tube format. Also notice the general stability and ease of use. The Mini is intended to be simple, reliable benchtop tool for labs that want predictable evaporation without complexity. So we will start with obviously highlighting a very small footprint of that instrument and quite unique geometrical shape. The reason why we design this instrument with such a small footprint, it's obviously in the modern lab, every inch of the benchtop, it's costing money. So that design was done specifically into the orientation of creating the significant cost saving for end users. And I will show you in a minute why we got such a interesting shape of the front. So starting with the flow meter, you can control the flow by simply just doing that anti-clockwise. The Mini could achieve the pressure or flow of 90 liters per minute, and the minimum required flow is 30 liters per minute. I mentioned about interesting shape. The reason why it's done that way, it's because we obviously want to make sure that the flow meter is easy to read for the instrument, for the operator, and this is why there is a specific angle. The next things which I would like to demonstrate, it's how easy it is to set up the temperature. So at the moment we got 30 degrees, we will go quickly into the 40 degrees, and you will notice that with the matter of time, the instruments in a minute will start increasing the temperature. And obviously another parameter which is important, it's the actual footprint of the consumables which could be used with our instruments. So everything what is in ANSI standard, SPS standard, SLAS standard could be used with our instruments. In this case, I will show you the rack of 48 vials and obviously dedicated needle head, straight needle head, which is already fitted into the instrument. So I will put that quickly here, and you can see how easy it is to raise the height. Obviously, every time when you're doing this, you need to make sure that the center of the needle is directly inside of the well of your plates of the glass vials. The instrument is also quite easy to swap the needles. We operating those instruments with the standard needles in a format of 12, 24, 96 and a 384 well format. It's basically just 2 screws to change the needle, and that way you can use one base instrument and you can basically run multiple applications. Now I will jump into Mistral and Mistral XT150. The Mistral XT and Mistral XT150 is the instrument of choice for labs where evaporation is a bottleneck and the direction of travel is clear, which is automation and integration. So in this demonstration, I will quickly run through some software options, and obviously I will highlight the main reasons why this is #1 choice from the integrator's perspective. So again, I would like to highlight the footprint and a very simple ergonomic design. Again, there is a reason behind this. Those instruments could be run in parallel. So you can basically run, if you imagine on this bench, 5 instruments side by side, they're taking the minimum space required, and they can be all operate through one system. But also this square shape gives us a nice option of fitting that instruments into actual liquid handling instruments. Now I will show you a few options from the system perspective. So instruments, it's very easy to control. You got three basically stages: operator, administration, and custom option. I will quickly go to the operator, and then I will show you a little bit more what it's possible to do from the administrator perspective. So operator is the most simple access. Operator could choose up to 15 different programs, but those programs already locked, and operator cannot do any changes from the perspective of time, flow, or the temperature. The beauty starts in the administration mode. I will quickly put our secret password. And now select, choose the method. From that perspective, administrator could control start position. So this is where it's your basically home position for a plate. In this case, obviously, that is the home position. And the end position is how far plates will travel up and what will be the settings of the time, temperature, and the flow. So as I mentioned before, you can control the time also. So for each of the steps, you can set up the time. So basically, that's the time when it's the plates or the glass vials rack will go from the A position to B position. Then you can control the temperature as well. Important factor of this instruments. The previous instruments, UltraVap Mini, the operating temperature is up to 60 degrees. UltraVap Mistral, UltraVap Mistral XT150, and Levante could go up to 80 degrees. Okay. When the operator set up all the parameters, he can run the obviously method. But before we will do this, I will show you one more important thing, which is obviously loved from the perspective of integrators, is that removable shuttle. So that removable shuttle is basically one of the game changers of the market. What it does, it's basically preparing sample for the liquid handling instruments for the robotic arm to move from the A position to the B position. That's one of the features for the integrators. And the other feature is obviously the connection via RS-232 cable, which give you the full access to the IP and the control of this instrument. Now, we will close this and we'll put that into the run mode. With this instruments, we didn't think only about the integrators. We also think about the standard users. So you got 2 features built in for the operator to check what's actually happening with your sample. #1 is the light. So you can see what is actually happening to your sample
if the distance between the needles and the sample is correct, if there is any more time required for evaporation process. And the other feature is pause mode. So this is additional feature when, if you're not happy with the lights, if you still don't believe what actually happened in the samples, you can physically stop the program or put the pause mode into the program, check what's happening, step back, and press continue. Okay, now I will show you what you can actually see from the perspective of the screen. So on the screen, you can see the nice graph and two details. So first of all, this is actual temperature. So this is the temperature which was set up in the method, 40 degrees. And as you can see, it's quite stable. Now we got actual flow. This is 85 liters per minute at the moment, and the actual position of your plate. On the graph, as per method set up before, you can also see the total distance to travel, for example, and also the time. Now, I would like to highlight one more feature of this instrument, which is extractor connection. So the instruments got built-in fan here on the back, and you can connect this instrument to your extractor system, or you can keep that instrument in your hood cabinet. What that do is actually keeping the constant flow of the fresh air inside the instrument. That's way removing all the vapes and concentrate in this area, and obviously making the evaporation process a little bit quicker. Okay, the final instruments which I'm going to present today is a Mistral XT150, a lot taller, a lot bigger than other our instruments, but there is a reason behind. So this instrument is designed to keep, as you can see, a lot higher plates. In this case, we got a rack of about 100 millimeters plastic tubes. That instrument is designed for actual object up to 150 millimeters. Again, got exactly the same feature as UltraVap Mistral. It just gives you a lot more capabilities from the perspective of processing larger samples. Saying this, I would like to obviously thank you for this live demonstration and just highlight the one point that as we're selling our standard instruments with standard heads, in a PSL, we got full capability to make those instruments custom, and we can do the custom heads, and we can run the custom racks or holders for any labware.